Okay. Hello everyone, I'm Shushmita Rani Shah. Now I'm going to discuss about the Bellman-Ford algorithm, which is included in design and analysis algorithm course. So let's see which topic will be discussed in my presentation. First of all, we can see here the history of this algorithm and then the definition and then the purpose of this algorithm. After that, I will discuss about details of this algorithm, and then we can see here the simulation and then implementation in IDE. After that, we can see here the sample of input output, and then I will discuss about complexity and then the conclusion, and finally we can see here the references. Okay, now I am going to talk about the history of this algorithm. The algorithm was first proposed by Alfonso Simbel in 1995, but is instead named after Richard Bellman and Lizard Ford Jr., who published it in 1958 and 1956 respectively. And that's why this algorithm is called Bellman-Ford algorithm. Uh, Come here to the definition part. So what is this algorithm? Bellman-Ford algorithm is an algorithm that computes shortest path from a single source vertex to all other vertices in a weighted graph. So let's move on the next part of this algorithm. Why should we use this algorithm, or what type of problem can be solved using this algorithm? So let's see. Bellman-Ford algorithm has several real-world uses case, including it's especially used in the graphs where negative edges weight, where has negative edges weight, and finding negative weight cycle. And now we can see here an example, and that is a Google map. A Google map may use Bellman Ford for finding shortest path. And come here, the algorithm part. First of all, we can see here the Bellman-Ford function, and in this function, step one, here has an initialize step. In this step, I will initialize every distance of vertex is infinity, and parent of every vertex will be null, and the distance of source is zero. After that, we can see here the relaxation part. In this relaxation part, I iterate loop from 1 to vertex minus 1 times. And in every iteration, I relax every each and every edges if distance of u plus v, I mean distance of u plus w, I mean weight is less than distance of v, that means distance of destination node, then we will update distance of v is equals to distance of u plus weight, and parent of v is equals to u. And then the step 3 is checking part. I iterate this loop one more times for checking negative cycle. If distance of v, even then will update, then it will return false, otherwise true. So it may not clear for us. Let's see an example and make it clear. And that is our graph. Consider this graph as an example. So as said in the algorithm part here, we can see the initialization part, like every vertex will be infinity and source node will be 0. And after that, I want to show here the order of relaxation. Uh, you can relax uh, you can relax these edges any order, any kind of order, that is you can relax D to B before B to A, and so on. So let's start fast pass and fast relaxation, and that is B to A. B is infinity and edge is 2. So infinity plus 2 is equals to infinity, and E is already infinity. That's why E will not update. Second relaxation, B, D to B. and that is infinity plus 1 is infinity, and v is already infinity, so it also will not update. Third relaxation, that is b to d. Infinity plus 2 is equals to infinity, and that's why d will not update. And then the fourth relaxation, that is 0 minus 1 is equals to minus 1, and minus 1 is obviously less than infinity, and that's why b will be minus 1. After that, a to c, and that is 0 plus 4 is equals to 4, and 4 is obviously less than infinity, and that's why c will be infinity, c will be 4. Sixth relaxation, that is infinity plus 5 is equals to infinity, and infinity is obviously greater than 4, and that's why c will not update. And seventh relaxation is minus 1 plus 3 is equals to, and 2 is obviously less than 4, and that's why c will be 2. Eighth relaxation, that is infinity minus 3 is equals to infinity, and d is already infinity, that's why it will not update. And after first pass, our graph is look like that. Then the second pass, first relaxation, that is same as first pass. Minus 1 plus 2 is equals to 1, and 1 is obviously less than infinity, that's why u will be 1. And infinity plus 1 is equals to infinity, and infinity is obviously greater than minus 1, that's why it will not update. And third relaxation, that is b to d, minus 1 plus 2 is equals to 1, and 1 is obviously less than infinity, that's why d will update. And fourth relaxation, that is 0 plus 4 is equals to 4, and 4 is greater than 2, that's why it will not update. And then 1 plus 5 is equals to 6, and 6 is obviously greater than 2, and it remains same. And minus 1 plus 3 is equals to 2, and c is already 2, that's why it will not update. And seventh relaxation, that is 3 minus 3 plus 1 is equals to minus 2, and minus 2 is obviously less than 1, that's why d will be minus 2. And after first pass, if we iterate these loops 2 more times, we can see here not update, not changing in this uh, vertex. And we get our value is minus 1, 1, and minus 2 and 2. So here we can see a negative cycle graph that's look like this. And if our graphs contains negative cycle, then our algorithm returns false. Here is the implementation part of this algorithm. Actually, I use matrix or two-dimensional array for implementing this graph, but if you want to use list, then you can. But I think it is easy process, so let's make understand. As I said in algorithm part, here we can see a Bellman-Ford function, and in this function we can see the initialization part and relaxation part, and here is checking part. Initialization part I initialized here. Every distance is max value, that means infinity, and parents will be minus 1, that means null, and distance of source will be 0, that is uh, so it is 0. And here relaxation part, I will iterate this loop how many times, that is v minus 1, I mean vertex minus 1 times, and every relaxation part I will relax every each and every vertex. And here we can see this if condition, and in this condition, if we can see if v distance of v is less than distance, greater than distance of u plus weight, then we will update distance of v and parent will be u. And here the checking part, I iterate this loop one more times, and if our distance of v will be updated, then our algorithm returns here negative edges cycle is found. So here is the print here I used this for loop for print our uh, graph and distance of graph. And in the main function, um, here I want to get input from user, and that is the weight of every edges. And I used here in two if condition. And what is this condition? What I have done here, if v is equals to u, that means that is same, if that is same nodes or same vertex, in weight will be 0. And if weight is 0, that means there have no uh, edges in these two nodes, then weight will be infinity. And here I call Bellman-Force function. After that, we can see here input and output sample. And first example denotes our first graph, that is look like it. And second example is denotes our second graph. And our algorithm reports us that here have an negative edges cycle. So here I want to show here complexity. And that is, first of all, I want to explain time complexity. For initialization part, complexity will be order of order of V. And for the relaxation part, that will be order of V minus 1 into E, and that is VE minus 1. And we know that VE is greater than E, and that's why our complexity will be order of V into E. And for checking part, it will be order of E. Overall, we can see here VE is greater than others, and that's why our time complexity will be order of VE. And space complexity will be order of V, that means how many vertex will input it. And here we can see a table of time complexity. That is best case, this time complexity will order of E. In average case time complexity will be order of V into E, and worst case it will be order of V into E. And here the conclusion part. In this article, we have used knowledge from previous two article on relaxing edges and detecting negative cycle to implement Bellman-Ford algorithm. We can say it is more flexible than Dijkstra's algorithm because it can handle graph that has negative edges and if there is any negative cycle in this graph, so it will inform us. And we can say this algorithm is byte slower than Dijkstra's algorithm, and it cannot work with the graph that has negative cycle. And finally, here the references. Actually, I watched Linta Man's lecture video and get total idea on this algorithm. And I used these two websites for collecting pictures and history. And finally, I want to thank Linta ma'am for giving me such opportunity.
Hello everyone, thank you for joining me here today. Uh, my name is Abhishek Dasgupta, Department of Computer Science and Engineering. Today I am looking forward to talking to you about Prim's algorithm on minimum spanning tree. So let's start. Let's first see the contents. Here the first one is introduction. Then we'll talk about minimum spanning tree. Then we'll talk about Prim's algorithm. Then we'll talk about the code, the output, and the complexity analysis, and the applications where it's used, and advantages and disadvantages, and at last the summary, and of course the reference. So first of all, the introduction. Prim's algorithm is a greedy algorithm that finds a minimum spanning tree for a weighted undirected graph. Uh, Developed in 1930 by Czech mathematician Wojtek Zarnik and later rediscovered and republished by computer scientist Robert C. Prim in 1957 and E.W. Dijkstra in 1959. Therefore, it is sometimes called as DJP algorithm, Jarnik's algorithm, the Prim-Jarnik's algorithm, and the Prim-Dijkstra algorithm. Now, the minimum spanning tree. Given a connected and undirected graph, a spanning tree of that graph is a subgraph which is a tree and connects all the vertices together. A single graph can have many different spanning trees. A minimum spanning tree is a tree less than a spanning tree with weight less than or equal to the weight of every other spanning tree. If a graph has n vertices, then its MST graph will have n minus 1 edges. We'll clear about that in the next example. So here you can see a graph called G, which has 4 vertices and 6 edges, and its total cost is 21. And you can draw the either of the MST graph. Here you can see in the last 3 graphs are the MST graphs. You can draw either of them. The costs will be less than the main graph. The MST graph's cost will be less than the main graph. Here you can see the cost is 7 and the edge is 3 edges, and there are 4 vertices you can see in the graph G. And so you can say if there are 4 vertices in graph G, in the MST graph there are 3 edges, and it goes same for the last 2 graphs too. Here you can now we're going to see an example to understand Prim's algorithm. At first we declare an array named MST list and consider the open list as a priority queue with minimum heap. And adding a node its edge to the MST list indicates we have found an edge that links to the node into the minimal spanning tree. As a node is added to the MST list, its successors are examined and added to a priority queue of open nodes. We will clear about it in the next example. Here you can see the main graph. Here there are 7 nodes. You can see we can start from any node. So I'm going to start from 3. So we're going to put 3 in the open list. As we started 3 from the as we declared 3 as the root node, so we're going to put it in the empty list. Now we will see all the adjacents of 3. There are 4 adjacents of 3, and the 3 to 0, 3 to 1, 3 to 4, and 3 to 5. Here, if we go from, and now we have to find which adjacent holds minimum weight value. If we go from 3 to 0, then we'll get the minimum weight, which is 5. So we're going to put 0 in the MST list. The remaining ones are 1, 4, and 5. You can see 0 has 1 adjacent, that is 1. The remaining adjacents of 3 are 4 and 5. So we're going to put that in the open list. So we're going to find the next node, which we can find from among 3's adjacents and 0's adjacents. So next we can see that if we go from 3 to 5, the minimum weight is 6, which is minimum than the other nodes. So we're going to take 6, we're going to take 5 as the next node, and we're going to put it in the MST list. Here now you can see 5 has 2 adjacents, 5 to 4 and 5 to 6, and 3 has 2 adjacents, 3 to 1 and 3 to 4, and 0 has 1 adjacent left, that is 1. Here among all these adjacents, now we're going to find the next minimum weight node. Here you can see if we go from 0 to 1, where the minimum weight is 7, the weight is 7, which is minimum than the other nodes. So we're going to put 1 in the MST list. So the remaining open lists are 4, 6, and 2. If we put 4, 6, and 2 in the MST list, then MST list will be complete. That means the MST graph is complete. So we're going to find the next one among these adjacents So next, if we go from 1 to 4, then we will find that weight 7, which is minimum than the other nodes. So we're going to put we're going to put 4 in the MST list because 4 contains the value 7, which is minimum than the others. The next the next we're going to do next is 4. If you go from 4 to 2, there is an adjacent of 4 is 2. There's an adjacent of 1 is 2. So for next, whose value is who contains minimum weight. If we go from 4 to 2, 4 to 2, whose value is 5, then and if we go from 1 to 8, 1 to 2, then we will get the value 8, whose value is minimum. If we go from 4 to 2, the value will be minimum than 1 to 2 has. So we're going to choose 4 to 2, whose value is 5. So we're going to put 2 on the MST list. So the remaining node is 6. We can go to 6 from 4 to 6 or 5 to 6. 4 to 6 contain the weight 9, and 5 to 6 contain the weight 11. So we're going to take 4 to 6 as it contains the minimum weight. So you can see I took 4 to 6. We took the road 4 to 6 as it is whose value is 9 and it is minimum and it is less than 11. So now you can see the MST list is complete. We put all the nodes in the MST list. So you can see the MST graph of the main graph. And now here we are going to start the algorithm. First, there is an MST prim function in the start. For each u belongs to g dot v, where u is the vertex, the root vertex, you can say. At first, initially, all the keys and all the key means weight of all the vertices. At first, initially, all the keys will be infinity, and u dot pi means parents. At first, all the parents, nobody have any parents, so u dot pi is nil. So when we start, we have to first choose the root node from where we will begin the MST graph. So we're going to choose r dot key as the root node weight. Root node weight will be 0 initially. Then q is equal to g dot v. Q means q means all the vertices that are not in the MST list, that is q. So g dot v is all the vertices are not in the MST list initially. So while q not equal to 0, that means while q is not in the MST list, we will take u as the extract minimum q. That means we will take a node from minimum q and we will put it in the MST list. For each v belongs to g dot adjacent u, that means all the v that are the adjacents of u. And if v belongs to q, that means if the adjacents belongs in the q list and the weight of that q less than the previous one, that means at first it was infinity. That means we will take 4. If we take then that means any value is less than infinity. So we're gonna write v dot key, but that means a new value is wuv, and the v dot pi is equal to u. That means the v dot pi's parents is u. That's how we're gonna do the program. Here you can see a connected graph G and the root R of the MST to be drawn are inputs. During the execution of algorithm, all vertices that are not in the MST reside in a mean priority queue based on key attribute. For each vertex V, the attribute V dot key is the minimum weight of any edge connecting V to a vertex in a tree. So when the algorithm terminates, the MST graph A will look like V comma V dot pi. V belongs to V minus R. That's how we're going to do the algorithm. Next, we're going to see the code. First, we go to the main function. Here we can, in the main function, we called an object called T, and in the integer graph, we're going to put all the values as the adjacency matrix in an adjacency matrix way. So you can see in the adjacency matrix from 0 to 1, there you can see the adjacency matrix from 0 to 1, there is a value 7. From 0 to 3, there is a value 5. So we're going to put all the values in the graph, and we're going to print it through by calling the object premMST graph. So let's go to the premMST graph, premMST function. In the premMST function, you can see there's an integer graph, integer graph, and integer parent. We're going to first initialize the parent, then we are going to put weight as key, and boolean MST set as if it is as if we're going to put boolean MST set to find out if the vertex is on the MST set or not. So at first, for initializing, we're going to do a loop for I equal to 0, I less than V. I less than V means we took 7 vertices, and so we're gonna it will go to 7. It's gonna scan all the 7 loops, and it's gonna take all the 7 loops, and it's gonna put the numbers there to initialize all the values from uh, of weight. You can see key I to integer dot max value. And initially, we're going to put the weight value, that means the key value, as infinity initially, and the MST set is false because none of them are not on the MST list at first. So as for taking the root node, as for starting from the root node, we're going to take key 0 equal to 0. That means the first root node's weight is always 0 initially, and there is no parent of the root node. So we're going to take parent 0 equal to -1. Then we're going to count from 0 and count from 0 to V minus 1. Why we took V minus 1? Because if there is V vertices in the graph, there will be V minus 1 edges. So it will count from V minus 1, it will run to V minus 1 times. So then V minus 1, then count plus plus, then U equal to minimum key. We will go to the minimum key function now. In the minimum key function, you can see at the beginning, we took integer min dot integer max value. That means we took all the values as maximum, and the minimum index equal to -1. That means the first minimum index will be -1 because we don't know nothing about at the start. We don't know nothing about the position or the minimum vertex of the graph. So now we will do a for loop from we're gonna do a loop from V to 0 to V less than V. That means we're gonna loop from V to 7. There here you can see we took 7 vertices. Then if MST set equal false and the key V less than minimum, that means if the MST set equal false, that means we have to keep the MST set false, because whatever vertices we are choosing, the that should not be in the MST list, and its value, and if its value is less than the previous value, then we will take the new value. We will take the minimum value we will take the minimum value for the we'll take the minimum value for the vertex, and then the minimum index equal to V. That means whatever the whatever the score for that vertex, will put that, whatever the weight for the vertex is, we'll put that in V. And then we're going to return this to the minimum index value. where it has to be false, and it has to be MST set has to be false, because we have to be careful that it is not included in the MST list. And then after that, in the you can see at last, if MST set u is equal true for integer v equal to 0 and v less than v, that means we're gonna scan all the vertices and gonna see there is an edge between one vertex to another. That means graph uv not belongs to 0. That means there has to be an edge between them, and MST set equal false. That means the vertex should not be in the MST list, MST set, and the graph of uv, that means if the graph, if the vertices weight is less than his previous weight, then we are gonna, we will put the new weight to the vertex, that is key v equal to graph u and v, and the parent v is equal to u. And that means the new parent of this vertex will be u. And now we're going to print MST. We're going to use print MST function to print the values, to print all the edges, and it will run from 1 to for integer I equal to 1, I less than v, and that means it will scan all from 1 to 7. 7 means all 7 vertices, and it will print all the edges that are in the MST graph. So next, we're going to see the output. Here you can see the output from 0 to 1. There is an edge weight. Then 4 to 2, there's an edge of it. The output will show all the weight, all the edges that are in the MST graph with the weights. Next, we're gonna analyze the complexities. Here you can see for time complexity of adjacency matrix in searching will be order of v dot v. But for the binary heap and adjacency list, it will be O E log v. For Fibonacci heap and adjacency list, it will be O E plus v log v. For the best case, that means the sparse graph where E, that means E means the edge and V means the vertices, where E less than equal V, then it will be O V log 2V. For the average case, it will be O E log 2V. For the coarse case, that means the dense graph where E is equal to V square, then it will be O order of V dot V log 2V. Next, the applications. You can see it can be used for design of a network. One practical application of MST would be in the design of a network. For instance, a group of individuals who are separated by varying distance wish to be connected together in a telephone network, because the cost of two terminals is different. If we want to reduce the expense, a Prim's algorithm is a way to resolve it. Electronic circuitry, electrical wiring network, water distribution network, cable TV network, etc. Connect all computers in a computer science building using least amount of cable. We can use Prim's algorithm. A less obvious application is the minimum spanning tree can be used to approximately solve the traveling salesman problem. A convenient formal way of denying this is to find the shortest path that visits each point at least once. And we can use this application of MST would be finding airline routes. The vertices of the graph will represent cities, and the edges would represent routes between the cities. And obviously, the farther one has to travel, the more it will cost. So MST can be applied to optimize airline routes by finding the least costly paths with no cycles. There are more applications. We can use the MST graph, MST algorithm, MST algorithm. That is to create high quality images, study of molecular bonds in chemistry, in cartography. Cartography means to draw a map, to sketch a map where we can find the minimum route. Then we can also do it in the geometry and also clustering and route or travel management. Advantages and disadvantages. Advantages, it is easy to understand, and the root node is selected so clear about the starting node. Disadvantages are the time taken to check for smallest weight or arc makes it slow for large numbers of nodes. Difficult to program, it can be programmed in a matrix form. Then the same weight may increase the complexity when one of the weights eliminated in a cycle. These are the disadvantages. So the summary is the Prim's algorithm is a greedy algorithm and is a special case of generic minimum spanning tree algorithm and operates much like Dijkstra's algorithm that finds a minimum spanning tree for a weighted undirected graph and is mainly used for a dense graph with lots of edges. So I took the reference from the book Introduction to uh, Algorithm by Thomas H. Corman, and websites are MathWorld, Wikipedia, and is unf.edu. And thank you very much. I did sincerely appreciate your attention today. Thank you so much for interest and attention.
Good afternoon. Welcome to my presentation. I'm Mohammad Mahbubul Haq, holding ID B180, 180, 30, 50, and 17. And course name Design and Analysis Design and Analysis of Algorithm. My presentation topics works on Dijkstra's algorithm. List contents I want to present. Firstly, I want to define Dijkstra's algorithm, then history of Dijkstra's algorithm, and after that I want to show you how Dijkstra's algorithm works, real life application of Dijkstra's algorithm, implementation of Dijkstra's algorithm, conclusion, and also reference. Firstly, Dijkstra's algorithm. Dijkstra's algorithm is an alternative algorithm that finds the shortest path from source vertex to all other vertices in the graph. Basically, it means that it finds the shortest minimum length from the source vertex to all the other of vertex in the graph. It does not work on graph with negative weights. Basically, it works on the graph with positive weights. Here we have find a restriction. It does not work on a graph on a graph with negative weights. It is also called a greedy algorithm because it always rely on local optimum. Now I want to start some history, small history of the Dijkstra algorithm. Dutch computer scientist Erzscher Dijkstra invented the shortest path algorithm, which is known as Dijkstra algorithm. One morning, Dijkstra was shopping in Amsterdam with his young fiancée. They were tired, and so they sat on the cafe terrace to drink a cup of tea. At that time, he was just thinking whether he could solve the shortest path problem to travel from Rotterdam to Groningen. Then he designed the shortest path algorithm. It was a 20-minute invention. Dijkstra thought about the shortest path problem when working at the Mathematical Center in Amsterdam in 1956 as a programmer to demonstrate the capabilities of a new computer called ARMEC. He published the algorithm in 1959 as a solution Prim's minimum spanning tree algorithm. On the next slide, I will show how Dijkstra algorithm works. Basically, to understand this, we need to follow only 4 rules. Make sure there is no negative edges. Firstly, I want to show this in the weighted graph. In the weighted graph, let the source vertex A, and make sure there is no negative edges. If we saw the graph, there is no negative edges because there is no negative weights. Set distance. First of all, we need to set distance to source vertex as 0, because if we travel from A to A, then there will be no distance. It will be 0 from A. firstly, we need to, what we need to do is, we put all the vertices as on the row, and we source, if we travel from source vertex to source vertex travel from source vertex to source vertex, then there will be then there is basically there is no distance, and so we mark the distance 0 from A. We already visited this visited these vertices rule, and if we saw this is if we saw so from source vertex to if we travel from source vertex to C, then there is a direct way, and from A to C we need to travel 2 units. So we mark the 2 from A. And A to D there is a direct way, so we mark the distance from 6 units from A. And A to B there is a direct way, so we put the distance 2 units from A. If we travel from A to E, there is no direct way. We can and go through vertex C or vertex D or vertex B, D, F. So we put the value as infinity distance, infinity units from A. And if we travel from A to F, there is no direct way, so we put the value infinity from A. Rule 2 is basically relax all the vertices to the current vertex. Relax all the vertices adjacent to current vertex, which means that uh, if the vertex adjacent vertices have direct way, so we mark the value here and here, and chose the closest vertex as the current vertex. Here we have already visited A, and all these black, which I marked as black color, are unvisited. From unvisited, we need to check which value is smaller. Here B and C value is smaller, so we can and take B or C. Next I take B. I'm working with B. So uh, I marked already, I already write down the visited part, visited, and 2 is already visited because B to B there is no distance. But why 2 from A? Because we have already traveled. If we want to find the B vertex, we have already traveled from A to B 2 units, so we mark it 2 from A. Then and B to B to C there is no direct way, so we are not going to update the value. We put the value as same as before. B to D there is a direct way, so and from if we travel from B to D we need to travel 1 units. As I say before, we already visited B. We if we want to find vertex B, we already visited from A to B 2 units. So 2 plus 1 will be 3. 3 units from B. From B vertex to E, there is no direct way. So we put the value as infinity from A, and B to F, there is no direct way. So we put the value as infinity from A. Next, here these two are visited, which I marked as red color, and from the unvisited part, we will check which vertex is which value is smaller. Here we will see C is smaller because it is 2. Obviously 2 is smaller than 3, so we will then work with C. so we will then work with C. We'll then work with C. I I have we already visited 0 from A, 2 from A, and C from and 2 from A, because if we travel from C to C, there is no distance 0, and we already, if we want to find the vertex C, we already traveled 2 units, so 2 plus 0 will be 2. Then if we want to travel from C to D, there is a direct way 4, and 2 plus 4 will be 6 unit. 6 unit. As 6 unit is greater than the previous value, so we will not update the value. So 3 units from B, and C to E, there is a direct way, and if we want to travel from C to E, we need to travel 5 units. We have already traveled 2 units, so 2 plus 5 will be 7 units from C, and there is no direct way from C to F, so we will put the value as infinity from A. We will not update it. We have already visited A, B, C vertices. Then we, from the unvisited vertices, we will check like which value is smaller. Obviously 3 is smaller than 7, so this is located in D column. So we will work with D vertices. I already wrote down the visited vertices: 0 from A, 2 from A, 2 from A, and 3 from B. 3 from B. As I said, we have already we have already visited from A to D. We have already visited 2 plus 1, 3 unit. D to E, there is a direct way. So we will have A to D is 3 plus 3 will be 6 units from D. 6 units from D. 6 units. As 6 units is smaller than the previous value 7, so we will update the value and put it 6 units from D, and mark the value as 6 units. Then, and there is a direct way from D to F. So D to F, if we travel from D to F, we will have to travel 2 units. So 2 plus 1 will be 3, and 3 plus 2 will be 5 units from D vertices, 5 units from D vertices. Here we already visited A, B, C, D. Now we will have to check the unvisited or unexplored vertices and check which, obviously here 5 is smaller than 6, so we will work with F vertices. So we will mark the F vertices as visited. So I mark it as red color. If we travel from F to F, there will be no distance 0, but from A to A but if we travel from A source vertex to F, we already visited 2 plus 1, 3, and 5 units from D. 5 units from D, and 5 units from D. So we will mark. So there is only, we have explored all the vertices except E. So as E is unvisited, so we will now work with E. E to E, there is no direct way. So we have already visited. Sorry, I have skip one thing. D. If we travel from F to D, if we travel from F to if we travel from F to E, there is a direct way, and we need to travel 1 units. So 1 units, we need to travel from 1 units. F to E is 1 unit, but F is already 5 units, so 5 units will be 6 units. So there is no update will be required. In the next, we will work with E vertex as E vertex. As I say, from E to E there is no distance, and So 6 plus 0 will be 6. I have explored all the vertices A, B, C, D, E, F. I have explored all the vertices. Now on the next slide, after visiting our exploring all the vertices, we will see that if we want to find the vertex B, if we want to find the vertex B, B is visited. So B is coming from A. Look at here, B is coming from A because 2 from A, 2 units from A. So B is coming from A, A to B. Shortest path is A to B, and path length is 2 units. And if we if we want to find find C vertex, we will see C vertex here row wise and column wise. C is here, so it is coming from A. So shortest path will be A to C and 2 units. And if we want to find D vertex, then we will show that row wise D and column wise D is here, 3 units. 3 units is from B. It is coming from B, and what we will see after this, B is coming from A. So our shortest path will be A to B, and B to D is 3 units. If we want to find the vertex E, then our shortest path will be here. E row wise E is here, and column wise E is here. 6 units from D. It is coming from D. So E is basically coming from D, and it is shortest length is 6 units, and E is coming from basically D. And here we see D is coming from B, and B is coming from A. So our shortest path will be A to B, B to D, and D to E is equal to, and path length will be 6 units. If we want to find F vertex, so if we want to find F vertex, we will check like row wise F is here and column wise F is here. So 5 units from D. And if we check D, row wise D is here and column wise D is here. D is coming from B. And if we check B, B is coming from A. So our shortest path will be A to B, B to D, and D to F, and it will be 5 units. If we check, I check it once again. A to B, B to D, D to F is equal to 5 units. A to B is 2 units, and B to D is 1 unit, so that it will be 3 units, and D to F is 2 units, so it will be 5 units. This is how Dijkstra algorithm basically works. Next, as real life application, I want to say it is widely used in maps, computer networking, or routing system. If you want to, if we want to log in Facebook or Facebook profile or something else, then it will go to what it will do, go to the shortest path to its root destination, where its server is. So it is widely used in maps and computer networking or routing system, etc. Next, I want to show you the implementation of the Dijkstra algorithm in Java using adjacency matrix. Basically, I am using Sublime Text because my laptop, I'm using Sublime Text, and I want to print the output in CMD. What I do first is, here I take a class as main, and take a class as main, and I basically first take the number of vertices is 6 vertices. I take the number of vertices 6. Then I am going to find a vertex with minimum distance. So I set a function. In the function, I set an array, path array, and Boolean shortest path set of array. It is used because we are going to initialize all the vertices as false. Next is on initialize. Then we are going to initialize as mean value. Here integer mean because so on the Dijkstra algorithm we saw that all the vertices as first here Dijkstra algorithm set distance to source vertex as 0 and set all other vertices to infinity. So we are doing what we are doing is set all the vertices to infinity by integer dot max value, because computer does not know the maximum value as infinity. So we are doing this, or we can also take 999, because we can consider this to the maximum number, and mean index equal -1. Then what we are doing, and we are doing a for loop of integer v equal to 0, and v is less than number of vertices, because number of vertices here is 6. We are going to 6 time using this loop, and v plus plus is the increment. If shortest path set is equal to false and path array is less than or equal to minimum, then shortest path set is equal to false. If there is no shortest path set, then and our path and path array is less than or equal to minimum, then path array will be mean will be the path array, and mean index equal to v, and we will return the mean index. Then what we'll do, path between vertex, and as I say before, if we travel from A to A, source node on the graph there, the source node was A. If we travel from A to A, there will be no distance, so we initialize the source node as 0. Then I know, and I'm going to find the shortest path for all vertices. So what I'm going to doing a for loop, integer count int count equal 0, count is less than number of vertices minus 1, because there will be the number of num vertices minus 1, there will be a if the vertices is 6, there will be 5 edges. So, and count plus plus. Next, I am going to call mean distance method. Mean distance method to find the vertex with mean distance. Int mu, int u equal to mean distance path array as shortest path set. The current vertex u is processed. Shortest path set of u is 2. Now I'm going to initialize the shortest path. If the shortest path set is u is equal to true, then process adjacent nodes of the current vertex. If shortest path set if the vertices is in the shortest path set, then and we will process adjacent nodes to the current vertices. For it, I'm doing a for loop, and I'm doing a for loop. If for loop, if vertex v in shortest path set is not in the shortest path set, sorry, I already skipped one thing. Shortest sorry, if shortest path, if vertices is in the shortest path set, then we will initialize the as the process the process adjacent nodes to of the current vertex. If vertex x v vertices are not in the shortest path set, then we need to update it. So what we are doing, and we are doing an iteration. If shortest path set is not shortest path set, and graph is not equal to 0, and path array is not equal to integer maximum value, which means that it is not equal to infinity, and path array u plus graph of is less than path array. Path array will be path array will be print path array plus graph graph. Then we are doing print the path array. Here I'm using my own on graphs 0, 1, 2 as 6 rows and 6 columns. Then I print. After printing, I get the output as like this. Vertex 0, for vertex 0 minimum distance is 0. For vertex 1 minimum distance from source. Obviously 0 was the source, from 0 vertex 0 to 1, which means this 0 to 1 will be distance we need to travel 2 units. Here is the output which I run on command prompt or CMD. And here I am going to say this time and complexity of Dijkstra algorithm is order of v plus e log v, and space complexity is order of v plus order of v equal order of 2v. In the summary, in the conclusion, we have learned what is Dijkstra algorithm is, how it works, where we can use it, how to implement the algorithm in Java using adjacency matrix. Reference I use Introduction to Algorithm, writer Corman, Design of Algorithm, writer Illumina Cosmina, and www.softwaretest.com. Thank you for watching my presentation, and special thanks to Lynn Taman.